Okay, so we're starting section 3.6, optimization, and let's look at the first example. So we have two positive numbers. We're looking for two positive numbers whose sum is 60 and whose product of one times the square of the other is a maximum. So now we need to set up some equations. So two positive numbers. That's where we're going to start. Okay, start here. So they are not necessarily the same number. So we're going to say let x be the first number and let y be the second number. Okay. So if their sum is 60, well, sum means that you are doing what? What does sum mean?
Adding.
Yeah, adding.
And are you recording?
I am recording, yes.
Okay.
Let me double check. Let me make sure. Yes, I am. All right, so we're going to do x plus y equals 60. All right, done. Got that taken care of. Now, the rest of this is saying whose product of one times the square of the other is a maximum. So that's a lot going on right there, kind of. Okay. So product means that we are multiplying, right? The product of one of them, we'll say x, times the square of the other, so this would be y squared, is a maximum. Okay? So just to clarify, because I did this example before, when he says 1 right here, he means the first number. He doesn't mean the actual number 1, okay? So this is the first, this should be the first number times the square of the other is a maximum. So you've got x times y squared. Now, there's like, you don't know what that's equal to. They're not telling you what that's equal to. So we'll just say that that is equal to P for product. Okay. Now they're saying that that is a maximum. That means that, you know, you're going to maximize the product. So right here, this means maximize the product. Okay. So in every single one of these optimization problems, you are going to have two equations that you are going to set up, okay, without fail. Every single time, you're going to have two equations. The first equation is like the helper equation. The second equation is the one that you actually maximize, like it's the one you're going to do the calculus with, okay? So in this example, the x plus y equals 60, this is the helper equation. All right. The second equation, this p equals xy squared, this is what we are going to maximize. Okay. So how do you know which one is which? It's always attached to the information. So if we go back and we read the word problem very carefully, it says whose product of yada, yada, yada is a maximum. The product is a maximum. So that's the thing that you are maximizing, okay? All right, so now this next part, this next step is using what you learned in 3.1 through 3.5. How do you find a maximum, right? If you want to find a relative maximum or a relative minimum, you need to take the derivative of the function and set it equal to 0, find some critical values, and make your number line, right? So this is where the old stuff that you've already learned, this is where you use that. Now, the problem is we're trying to maximize this function right here that has 2 variables, okay? We don't want 2 variables. We want to get it all into 1 variable. Otherwise, you have to take the derivative of this implicitly. And we don't want to do that, okay? It'll become too complicated. We won't be able to solve for the critical values if we have to take the derivative implicitly, okay? Are y'all with me, or have I lost you? Give me like a thumbs up or a check mark or like holler or something if I've lost you so far. Or I mean, like, you know what I mean, if you're okay. All right, okay, so almost everybody. Don't be afraid to speak up if there's a part where I lost you. So let's go back, let's just talk it out one more time. We're trying to maximize this equation right here. So in order to find a maximum, you have to take the derivative of this and set it equal to 0. Right now, it's in 2 variables. So we want to get it down to 1 variable. So that's where the helper equation comes into play. You are going to solve this equation over here for one of the variables. It doesn't matter which one, okay? So what would you like to solve this for, X or Y? No preference? Don't care?
Let's do X.
All right, sounds good. So X equals 60 minus Y. So everywhere you see an X over in the other equation, you are going to substitute 60 minus Y. Okay? That's how that helper equation helps you out. It helps you get the maximize equation all in terms of 1 variable. Okay. All right, so now we're good to go. We're all in terms of 1 variable. We need to maximize this. So we are going to take the derivative of it. Don't freak out with this P right here. It's just like saying Y equals, same thing. So this will be dP, and in this case, it'll be dy because Y is our variable. So the derivative of P with respect to Y. And then I guess we could do product rule, or this isn't really that bad. I think I'll just distribute it and use power rule. So this is 60y squared minus y cubed to begin with. What will the derivative of this be?
(120y minus 3y squared).
Excellent. All right, good. So we do that, set it equal to 0. You could also set it equal to dne to find where this derivative doesn't exist, But this is just a polynomial, so this is going to exist everywhere, so you don't have to worry about that really. Solve for y. So let's see here, what can we take out of 3y? And we get 40 minus y. Yeah, check me on that. And then, so then you set each factor equal to 0. So 3y equals 0 or 40 minus y equals 0. Divide by 3, y is equal to 0. Or over here, y is equal to 40. Okay. Okay, so now this problem is asking you for two numbers. And remember at the beginning, they had to be two positive numbers. So right now we just solved for y, but 0 is not positive. 0 is neither positive nor negative, so you throw that one out. So y must have to be 40 for this, okay? It's the only critical value, so you don't have to check if it's a max or a min. It'll end up being a max if you do the number line. But since this is the only one, it's not necessary to do the number line. So if y is 40 and we know x plus y has to add up to 60, x plus 40 adds up to 60, so x must be 20.
Wait, why did we get rid of the y equals 0 again?
Because the two numbers have to be positive. Said find two positive numbers, and so since that one's not, it's neither positive nor negative, you throw it out. Okay. Now let's say you kept it, like you didn't notice that little thing. If y is 0, then x plus 0 would be 60, and x would be 60. Now think about this. Yes, 60 plus 0 does add up to 60. But remember, the product is what we're trying to maximize. So this would be 60 times 0 squared, if I took this and plugged them in up here. And anything times 0 is going to be 0. So if it's 60 and 0, the product will be 0. If you do 40 and 20, the product will be 20 times 40 squared, which is 32,000, I think. 1,600 times 20. I think it's, I don't know. I think I did that in my head correctly, but you can check it. Whatever it is, it's bigger than 0. So you're trying to maximize the product, trying to get the biggest possible answer. So even if you didn't throw out the 0, when you plug it in, you'd see that this product answer is bigger than this one. So it must be 20 and 40. Okay. So the two numbers whose sum is 60 and whose product is the first one times the second one squared have to be 20 and 40. Any other questions? Ask me something else that has to do with this problem. No questions? So basically, the routine that you're going to follow is you're going to come up with the two equations. One of them is going to be your helper equation. It'll help you get the other equation all in terms of one variable, okay? Once you get that second equation all in terms of one variable, you're going to take the derivative of it and set it equal to 0. Solve it, and then plug back in at the end. Okay? That's all you're doing. 2 equations, take a derivative, set it equal to 0, solve. The hard part is coming up with the equations sometimes. All right, so let's look at example number 2. So this is like where the geometry is coming back to visit. So we have an 8-inch long pipe cleaner. And it's bent into the shape of a rectangle. So they've got like this 8-inch long pipe cleaner, and they're gonna bend it so that it does this, okay? So like bend your pipe cleaner so that this 8 inches wraps around a rectangle. What dimensions of the rectangle will produce the rectangle with the maximum area? So we are trying to maximize area. So tell me, what is the formula for the area of a rectangle?
Length times width.
Yeah, length times width. So let's put
Yeah,
it out on here, and let's put a W right here. So just to be proper, let's let L be the length and W be the width. If you want to use base times height, that's fine too. Whatever you want to use, okay? All right, so we are trying to maximize the area. So A equals L times W. This is the thing that we are maximizing. So the area formula is going to be what we end up taking the derivative of. Okay. This is what we're going to end up taking the derivative of, setting it equal to 0. But right now, you got 2 different variables. So I need another equation from the given information that's going to help me get this into one variable.
Well, length plus width must equal, no, 2 length plus 2 width must equal 8, right?
Very good. What does 2L plus 2W represent?
How many inches we have to work with?
Yes, and specifically it's the perimeter, right, of the rectangle. We know that this 8-inch pipe cleaner was bent so that it would form a rectangle. So all the way around the rectangle has got to add up to 8 because that's all we've got to work with. Okay, so this is your information from the given. Okay, this is what's going to help you. Now, it doesn't really matter what we solve for because we need to know the dimensions. Like we're going to end up having to solve for the length and the width. So it doesn't matter to me what you would like to solve for here. Anybody have a preference what you would like to solve this for?
Length.
Alrighty, let's go length. So we're going to subtract 2W. And then we're going to divide by 2. We're going to divide everything by 2. So length equals 4 minus W. Now, wherever you see a L over here, you are going to sub in 4 minus W. So A equals 4 minus W times W, like that. All right, so this is the thing that we are maximizing. So this is what we have to take the derivative of. So just like the last one, it's not too terrible to just multiply this out. So I'm going to do that. And then we're going to take the derivative. So this would be dA, dW. And then what's your derivative of that?
4 minus 2w.
Yep, good. Set that equal to 0. A maximum exists when the derivative is set equal to 0, because that would be where the tangent line is nice and flat at a max or a min. Solve for w. So -4 equals -2w. Therefore, w is 2. So if w is 2, and that would be 2 inches, then the length is 4 minus 2, and so the length is also 2 inches. And I don't know if you remember that from geometry, but the quadrilateral that's always going to maximize area given a set perimeter is always going to be a square. The square most efficiently uses the space for the perimeter that it's given. So that should always be a square.
Is this one of those things where it's like a rectangle can be a square, but a square can't be a rectangle?
Yes, the other way around, but yes.
Oh, yeah.
All squares are rectangles. They're special rectangles, but not all rectangles can be squares. Yeah. Okay. I used to teach geometry long time ago. That was like my first gig, my first like teaching job. They always give like the new person geometry. So I like geometry. Okay, example 3. Ladybug farmer has 500 inches of fencing and wants to fence off a rectangular field that borders on a straight river to enclose his grazing ladybugs. All right, so we got a fence. We're fencing in the ladybugs, but on one side, we have a straight river. There's the river. Here's the fence. So we're fencing in the ladybugs along a straight river. Now, he doesn't need any fence along the river. Ladybugs can't swim and that's disgusting, clipped his wings. What are the dimensions of the field that has the largest grazing area for his hungry ladybugs? So we're looking for dimensions again. That has the largest grazing area. So that is subtly telling you that you need to maximize area. Okay, so we know since it's a rectangle, and we just did a rectangle problem, that the area for a rectangle is length times width. So here's your length and here's your width. I'm trying to maximize that. So this will be the equation that I take the derivative of, but I can't do it right now because I have 2 different variables. So I need to come up with a helper equation from the given information to do some substitution. What what should the helper equation be?
Um, 2L plus 2W equals 500.
You're very close.
No?
We definitely need the equals 500.
Oh, because of the river. So
Yeah.
it would just be 2W plus L.
Right, good. 2W plus L. Okay. Now, this is not going to come out to be a square, you guys. This one's not a square. The reason that this one doesn't come out to be a square is because you're not using the other length of the quadrilateral, okay? So don't automatically think, oh, it's gotta be a square, because that only works when you have all four sides of, all four sides of the rectangle. All right, we're missing a side here, so this will not be a square. Okay, so we need to solve this for a variable and plug it into the area function. What would you like to solve for? Anybody? L, okay, let's solve for L. So L equals 500 minus 2W. Wherever you see a L in the other problem, put 500 minus 2W. So this will become A equals 500 minus 2W times W, like that. So then A will be 500W minus 2W squared. Take the derivative, dA dW. And the derivative will be 500 minus 4W set that equal to 0. Let's see, 500 divided by 4. 125? Yeah. So, inches. Make sure you put a label on these, okay? Because these are application problems. So W is 125 inches. L will be 500 minus 2 times 125. What does that come out to be?
L equals 250.
What was it? I didn't hear you.
250.
250. Awesome. So 250 inches. Okay. Any questions about that? Alrighty. Example number 4. Remember, if I'm ever going too fast or you don't get it all written down, just take a screenshot real fast and save it. You can look at it later. All right, example 4. Same ladybug farmer has purchased some expensive, extraordinary diva ladybugs who require exactly 10,000 square inches of grazing in order to be at their optimal ladybug-like state. What is the least amount of fencing required to get these diva ladybugs at their optimal state if the farmer is still allowed to build along the very straight river. Don't think diva ladybugs can swim and don't still have their wings clipped. Okay? All right, so we're still along the river. Still have the fence, length, width, still a rectangle. So now it's a little different. Requires, it says that the ladybug farmer ladybugs require exactly 10,000 square inches of grazing. What is the least amount of fencing required? Can somebody tell me one of the equations we need to use?
L times W equals 10,000.
Very good. L times W equals 10,000. So this time, square inches, right? That's the area. This time the area is set. Before, the area could be, could be big, could be small. But now we have a set area that we have to stick to. Okay? What's another equation that we will need to use for this problem?
Shouldn't it be like 2W plus L equals like P or something
Yeah.
like that?
Good, exactly. Which one are we trying to find a, let's see, least amount? I don't know, I don't want to say maximum because it's least amount. I guess we're trying to minimize. Which one do we minimize?
The 10,000 one.
The one with P.
The one with P.
Why?
That's the one that you don't know what it should be, and you're trying to find the least amount of fencing.
Okay, so fencing comes from going around the outside, right? Like if we were like putting like fertilizer down or something, that would be area, but fencing is around the outside. So that's got to be the perimeter. So since we're looking for the least amount of fencing, we are minimizing perimeter. Okay, so the one with the P over here, this is the one we're going to take the derivative of. But right now, it's in terms of two variables. So we go over to the other equation, and this is the one that helps you. Okay, so we are needing to find length and width, so it doesn't matter what you want to solve for. What would you like to solve for over here? L or W?
Length.
All right, so L equals 10,000 divided by W. Everywhere you see a L in the perimeter equation, you are going to substitute in 10,000 divided by W. All right, now I'm going to put the P over on the other side just because I'm a little OCD like that. So this is going to be P equals 2W plus 10,000 over W. This is the thing we're trying to minimize, so we got to take the derivative of this. So this will be dP dW And what will the derivative of that come out to be? Anybody have the derivative?
Is it 2 minus 10,000 W to the negative 2?
Yeah, that's exactly right. Very good. I'm going to put the negative 2 and put the W down the bottom like that. Now we need to set this equal to 0. So you could move the 10,000 over W squared over to the other side, and that equals 2. So then 10,000 equals like 2W squared, like that, multiplied by W squared on both sides. Divide by 2, so 5,000 equals W squared. Take the square root. W will be something. 50 root 2. I don't have my calculator. 50 root 2. 50 times 50 is 2,500 times 2. Yeah, I think that's right. 50 root 2. And that is going to be in inches. Okay. It doesn't really say if we have to have an exact answer. So if anybody has 50 root 2 as a decimal, just make sure you just put it out to 3 decimal places. Does anybody know what that would be as a decimal to 3 decimal places?
70.711.
Cool. Thank you. So that's in inches. And then we need to find the other one. So width, I don't know what's the easier one to work with, 50 root 2 or square root of 5,000? Probably this. So anyway, the length would be 10,000 divided by 50 root 2, which, let's see, knock that out. 1,000. 1,000 divided by 5 is 200. And then over root 2. And since it's calculus, you don't have to rationalize the denominator. You can just keep it like that. Or if you have a decimal equivalent, you can have your answer, just make sure you have 3 decimal places. And it doesn't say like here if we need to be exact or not. So I would take either answer. Anybody know what is, punch that in there. What's 200 divided by root 2?
Um, 141.421.
Thank you. Okay, there's your dimensions. Any questions about that one? Okay, all right, let's go on to the next one. Example 5. All right, so this one's not geometry. This one's some graphing, okay? And well, kind of geometry because you're graphing and you learned a formula that we're gonna use in your geometry class. So it's kind of geometry. Let's see what we got going on here. So find the point on the curve closest to 3, 0. So let's see here. Well, let's draw the curve. So this is x squared. We all should know what x squared looks like. It's a parabola with a vertex at the origin. I want to figure out what point on this parabola is closest to this point, 3, 0. So 3, 0 is somewhere on the x-axis, right here. Okay. So what point is going to be closest? Well, you might be able to visualize it kind of like it's obviously not going to be this point, maybe not this one, probably something like straight on, right? Like that would probably be the shortest distance. All the other like dashed lines that I would try to draw to the parabola are going to be a little bit longer than this one right here, right? So whatever this point is, it's on the parabola. So it'll be x, comma, y, right? And I want this point on the parabola to be the closest to 3, 0. So I'm trying to minimize, like I want it to be close, right? So what am I trying to minimize? What am I trying to minimize? If I want this to be, if I want this point right here to be the closest to that point.
Distance.
Yeah, distance, right. So we are trying to minimize distance. Which means we need a distance formula to take the derivative of, okay? And this is where it goes back to like your old geometry class. So distance formula, D equals, anybody remember it? Oh, all right,
Let me go grab my
Isn't it like the
pre-calc
square
book real quick.
of
it's okay.
x minus x2 minus y2 or something like that?
Kind of. There's a big square root. And then you got these things with, and that's squared. And then plus, and then you got these things. Squared. That's your distance formula. Way back, long time ago, probably for you guys, 8th grade, probably, or 9th grade, could be.
Or junior year.
Or hopefully not. Otherwise, you made up some really good time if you took geometry junior year.
You do it in pre-calc.
Oh, you do? Oh my goodness. Then, well, shoot, y'all should have been screaming that formula at me then. All right, that's okay. I won't tell Ms. Edwards. or Ms. Walters. Alrighty, so this is what we're trying to maximize. Here's the problem. It's in two different variables, x's and y's. I don't want to take a derivative of this until it's just either all x's or all y's, okay? Now, we do have some given information that will help us out for this. So we have this point right here. So we're trying to minimize this distance between the point and the point on the curve. So I could use the 3, 0 as one of my, like it could be my x1 and my y1. Okay, so I'll put that in. So 3 minus x sub 2 plus 0 minus y sub 2, like that. Okay. All right, it's looking better. Definitely does not look as nasty as the first one, the first in red, right? But I still have two variables. Like I still have x and y. So there is another equation that could be our helper for this. Does anybody know what it would be?
Could you replace y with x?
Oh, go ahead, somebody, I think you're both talking at the same time. It's okay. Somebody say what you were saying.
Y equals x squared.
Yeah, right here. Everywhere you see a y, put in the x squared. Perfect. There you go. So d equals 3 minus, now this little sub 2 right here, I'm just going to get rid of it because it's just going to get in the way, and I don't want, like, I don't want to end up using it when I take the derivative by accident. So I'm just going to call this a x. And then plus 0 minus, now that's where I'm going to sub this in. Wherever you see a y, put x squared. All right, perfect, very good. So now we just have to take the derivative of that. Like, you know, it's gonna be a little bit fun, but you can handle it for sure. So I'm gonna take, this is kind of weird the way it's like a d, but oh well, d dx, and go ahead. I'll just write down whatever you say.
Katie.
Bless you.
I'm okay. Not.
Come on, y'all, somebody be brave. Take the derivative of this.
Would it be like 1/2 and then you have everything under the radical to a negative 1/2? And then you have to multiply that by -2. Oh my God. Negative. So if you're going to take the derivative, the first like little parentheses part, it would be 2 times 3 minus x to the first power multiplied by -1.
Mm-hmm.
plus 2 times everything under that parentheses to the first power times negative 2x.
Okay? Yep.
Yeah, that's what I got too.
We're not done yet. We're not done yet. And so you could take it from here. So what do we have to do with our derivative, right? Set it equal to 0. You got a fraction set equal to 0. So what's the only part of the fraction that you care about?
The numerator.
top.
Yes, good. So I'm going to try to make some space over here and let's, all right, what's this going to turn into right here? This will be 2x minus 6. And then this will be negative, positive 4x cubed. Set equal to 0. Do I have that right? Let's take a good look at that. Yeah, that should be right. Yeah. Okay, so this is a cubic. I don't think this is going to factor. So I don't think that cubic is going to factor. Negative 24 adds up to 2. Yeah, the cubic is going to throw that off a little bit. So let's just go ahead and we'll get Desmos going here. So 4x cubed plus 2x minus 6. What you're looking for when that's set equal to 0 is you're looking for its x-intercept, which conveniently is at 1. Never would have guessed that. So x equals 1. Okay. So remember what the whole goal here is. It's to find the point on the parabola that's closest to 3, 0. So far we know that the x coordinate of that point is a 1. How do I get the y coordinate of that point?
You square it.
Yeah, put it in here, right? Put the 1 in right here because it's on a parabola. So 1 squared is 1. So the closest point to 3, 0 on that parabola is the point 1, 1. Alrighty. Nice job, everybody, you guys. We did 5 really good examples. So I am gonna call it a day and stop the recording. Let's see here. Here we go.